having looked into cement as the first thing, right, we looked into cement. Having looked into cement, first we looked into cement, OPC, their reduction and all that to make it more sustainable. Then we looked into water reduction, quality control, and somewhat related to concrete system, issues related to concrete system. So, one of them was, if you remember, natural resource depletion in terms of aggregates. Now, therefore, we should see how the aggregates, the role of aggregates and how we can reduce it down. Now, this is what I was showing you or telling you sometime related to strength. You will find that failure always occurs at the normal strength concrete, failures always occur at the aggregate mortar interface, aggregate mortar interface. You will rarely see in normal strength concrete the aggregate themselves are failing, unless you have very weak aggregate system, right. So, this shows the diagram of typical. So, failure through aggregate boundary rather than multiple rather than through them, and you will see multiple cracks. So, there are a lot of cracks. So, this is the shape of failed specimen. So, what actually happens is fracture starts from somewhere there and it will propagate to the next aggregate boundary, in between there are pores, connect through them. This is how fracture progresses. I think I showed sometime to those who did actually concrete technology course. Fracture plane is something of this kind. Now, you see, essentially, as I said, failure takes place through weak point. Okay, I do not know whether I have a slide here. ITZ I will come to, but do I have a slide? I think I do not have, because I am not talking too much about the strength here, but still those who have not done a course on that, for them, see the strength of such system starts from strength of such system. If I calculate out, for example, I know the calcium silicate hydrates, look at paste only. So, these bonds are they are layered structures, something like this, layered structures, something like this. These are kind of model people think CHS layer structure, and these bonds are covalent bond. Now, if there is a one layer, one sheet of this CHS, another sheet of CHS, between them there is gel, this is gelatinous in structure. So, we call it gel water, and their van der Waals bond exists between the two, right, van der Waals bond exists between the two. So, this one, if I want to calculate out the strength means I am trying to pull them, let us say, because separation of the material, this pulling. Shape of the cube failure, if you look at it, you applied load like this, right, and you had a shape like this, failure shape or something like this, right. That means some force must have separated the material in this manner, some force. So, if I take a long cylinder, that is better, I will not go into this now. Long cylinder, I will get, in fact, except for the small portion here, I will get fracture like this, crack, it would be something like this, failure shape would be something like this, except for small portion here, as if something has pulled it out along the other direction. That is Poisson's effect. So, failure of concrete under uniaxial compression is again failure actually due to tensile stress in the transverse direction, because it is weak in tension, and you can understand this very easily, because these are particulate material. You have bonded with some binding material, you have bonded with some binding material, these are bonded with some binding material, right, and which are not very strong. The bonds are not chemical bonds, they are mechanical bonds with the aggregate, interlocking sort of roughness, and in this. Therefore, when you try to pull them, this separates out. So, essentially tension they are weak, they are strong. If you try to push from all sides, triaxial test you do to the cube, they will simply get compressed. After that nothing will happen, it can take a lot of load. normal stress, as the normal stress you increase, shear strength also increases, you might have studied in solid mechanics. So, therefore, basically uniaxial compression means failure in tension. So, pull is dominant one, pull tension which will cause. So, if I look at CHS, this one, and look at this pull, now this forces, I can calculate out the van der Waals force, how much it would hold it on theoretically. So, how do I separate, or even all those bond strength, if I try to find out and calculate out theoretically, I will find the strength to be more than 1000 times than what we realize, more 1000 times more than what we realize actually we see in this kind of condition. Basically because there are flaws in the system, there are weak points, and this is why it is not only this fracture of material occurs, this is for brittle material, even for metals flaws are there, that is why you get all kind of deformation, etc., stress strain relationship and so on. So, this comes with the material flow. So, weakest link governs the strength, and what is the weakest link in this kind of system? Pores, because pores are inherent to cement hydrate system or this kind of particulate material system. Pores are inherent actually, inorganic bonded system. If you can remove them, strength will be very, very high. That is why Abraham got so much of higher strength, 0.8 water cement ratio, practically no water, very little water, coating only onto the cement particle, and it reaction would have occurred, reaction was taking place, and at that time he applied a lot of pressure. So, they actually all the particles get bonded together, unhydrated cement, because there will be a lot of unhydrated cement if you have so much of water. This unhydrated cement itself got bonded by the hydrated part. Now, you try to pull them, it is relatively difficult, it could take lot more load. So, that was the idea. So, these are the weak points in the system, right. I might have some equations there sometime later on. So, pores in the cement based systems, in fact, in geopolymers also you will have pores, although you are not using OPC clinker. All of this inorganic system, because whenever you are adding water to react and solidify, all the water, if if it is consumed and space filled by water, if it is filled by the solid product, then you will have no porosity, but usually that will not happen. If you are using polymer system, resin and or monomer some form or resins which will get polymerized to higher molecular weight and solidify, even there if there is a shrinkage of the polymer itself, you will get new pores. So, reaction process tend to or sometime even packing, etc., there might be already pores existing in the system. So, even polymers, etc., but generally polymers have got higher strength. There can be blowholes, air pockets inside. So, they are the weak points actually. So, that is why pores in cement based materials are important, because they govern the strength and of course, durability too, because if they are interconnected, as we talked about segmentation sometime earlier, then if they are interconnected, aggressive agents from outside may come and penetrate into it. So, the pores are important from larger pores, particularly capillary pores are important from strength as well as durability point of view. So, this type of ordinary Portland cement clinker system or Portland pozzolana cement, these types of micro pores have been identified, what are called gel pores, as I showed between the CHS layers. These are gel pores, shrinkage and creep they are responsible for. Capillary mesopores, these are the sizes, mechanical strength and durability they govern, and if you have air entrainment, deliberately you have put in air for durability purpose, for freeze-thaw resistance purpose, I will not discuss this. You can have larger pores also, or there can be some pores because of pore compaction. If you have pore compaction, this type of pores might come. So, therefore, in paste this kind of pores you will get, right, pores in cement based material, but in concrete you get additional pores at the interfacial transition zone. You get additional pores at the interfacial transition zone. What is interfacial transition zone? I think I have a diagram. So, I will come to that and then go back again. Supposing this is my aggregate, this is my aggregate, it says boundary, this at this boundary near this boundary, and these are my paste system, let us say. This zone properties are different than this bulk paste and this bulk aggregate as well. right. Why? Because I think next diagram here ITZ, this is around 30 micron or so people have actually measured. Now, let me see if I have bulk paste or mortar, if I have some more. No, okay, let me explain it here and then I will go back. Now, why this comes? If I take this portion and enlarge it, let us say, enlarge it a little bit, enlarge this, not happy with the color, enlarge this portion, then cement particles will pack here, cement particles will pack here. Packing is never very good near the wall. Cement, these sizes are, this will be millimeter size, 10 millimeter, let us say 5 millimeter, coarse aggregate if I take. Cement sizes are micron, 30 micron, 40 micron, 50 micron, lesser than that. So, micron sizes material here. So, therefore, the ratio you can see 10 millimeter and let us say or 30 micron. So, this 1000 times smaller or 100 to 1000 times smaller. So, this particle, this is like a wall, as if you have put in something in front of a wall, and packing there is never the best. This is called wall effect. Near the wall particles, otherwise in the bulk they will pack like this. In the bulk they will pack like this. Here the wall is there. Sometime this would block its going close to the wall. So, this is wall effect, right. So, wall effect is one of those effects which causes this. So, therefore, the properties here, the packing is not as good as this. Cement particle packing will not be as good as this. So, you have something called wall effect. We have something called one sided shrinkage effect, because cement paste shrinks, as you know. So, this side it will try to shorten, this will try to shorten, while this is not going to shorten. So, this whole bulk tends to shorten. So, there will be shrinkage. At the aggregate do not shrink, paste shrinks. So, therefore, shrinkage, due to shrinkage there could be some separation occurring. The third variety is the water, bleed water. If excess water is there, water might get trapped here at the aggregate interface. Water has a tendency to come up. In cement concrete system, water has got the least specific gravity. So, it will have a tendency to come up. And this is a regularly shaped aggregate. Supposing I have an aggregate of this shape something, water can get stuck here also. So water gets stuck at the boundary. So, wall effect, shrinkage effect, bleed water trapping as we call it, and also one sided hydration growth. The hydration will not occur along, hydration product will grow only in this direction more. This direction no hydration would occur. This direction here, of course, both direction hydration will occur. So, all of them put together, you get higher porosity in a 30 micron zone, which you will call interfacial transition zone ITZ, interfacial transition zone ITZ, which we call ITZ. So, therefore, this ITZ, ITZ is the other porosity which is there in concrete. In paste, these porosities are there. Wall effect, one sided hydration growth, shrinkage and trapping of bleed water, that is what I have mentioned. So, they cause additional porosity at the interfacial transition zone. And if you remember now the fracture part of it, it starts usually from the interfacial transition zone, right. In normal strength concrete, of course, in high strength concrete we try to improve that ITZ itself, because weakest link governs the strength. So, if I improve the ITZ itself, now maybe many things will fail together, a balanced situation. The fracture will start from a pore in ITZ or otherwise, and even might be a pore from the aggregate within aggregate itself, because aggregates are not zero porosity, rocks. So, all might start together. So, failure is at one point, therefore, failure is usually brittle, sudden failure, everything fails together. Here, of course, you will see a lot of deformation. So, that is what it is, pores. Now, my problem, what is the role on recycled aggregate? Yes, that has got a recycled aggregate, that has got a role. The strength of the concrete is governed by ITZ up to 70% of the ultimate strength, and cracking is largely due to ITZ cracks. This is 30 micron, as I said, and bleed water trapping below aggregate mentioned in connection with, okay, I am not talking about bleeding now, but I have explained you what this is. So, this is the aggregate motor interface, this is the aggregate motor interface, right, and that is the ITZ. Bulk porosity and pore sizes are governed by water cement ratio, bulk porosity, bulk paste porosity. ITZ porosity is more, and more pore sizes are also governed by water to cement ratio. Why? Because if you have higher water to cement ratio, at the ITZ itself the water will be more, and they are to be filled in by hydration product. So, therefore, this is also governed by water to cement ratio. That is why strength of concrete paste is governed by water cement ratio, strength of the concrete is also governed by water cement ratio, right. Same, higher the water cement ratio, strength will be lower, higher water cement ratio W by C versus strength, this is the nature of curve that you will get even in this case, even in concrete. So, that is the idea, that is the idea. So, aggregate, now this has got a relevance when you look at the recycled aggregate. Now, here what you do is, you see there is aggregate processing, you will find lot of photographs even in net if you search, and there are books of course. So, for example, these are they are reported by them. So, first the process is demolish demolition, construction waste, I can use them. Recycled aggregate is mostly based on construction and demolition waste or similar other products if I can get it from. So, this is first demolished, then collection, right, and then taking it somewhere else. After that, crushing using jaw crusher. So, this is crushing actually using jaw crusher, right, and then single jaw crushing, further crushing, crush to the required size as you would have done for aggregates. So, then separating using screens, larger size to finer size. There can be cone crushing after that. So, there are several stages of crushing of this demolition waste. In the meantime, you have to remove the metals, another product, right. So, if you have to remove, there are separating screen, there are magnetic roll crushing, all these are there, right, separating and roll crushing, separating through screen, and fine ones are separated out, roll crushing. So, this is process actually, and then fine particle oil separation, finer particle, because decantation rate, I mean the rate of particle going through the material through liquid, Stokes law differs. So, through oil you can do some separation, air blow separation for very fine particle, magnetic selector in order to remove metals, and then finally you might get recycled aggregates or something of this kind. So, from construction and demolition waste they would look like this, but let us see what are their properties. So, that is process, there are more. In Japan they do something more. Okay, I will come to this later on, I think I will come to this later on, but first processing Japan I will come to later on, but let me go to this one, explain what I was talking about. This I will not go, I will go into this, no, this is Euro classification, no, yes. So, old aggregate which is now I have got a new aggregate system. After crushing from the old concrete, I have got a new aggregate system, right, aggregate system, which will have some old aggregate and this old ITZ. And now the old mortar, so the sorry, the new aggregate, crushed aggregate, recycled aggregate will have old aggregate, interfacial transition zone of the old one, and the mortar adhered to it, because you have crushed it. Now, it is concrete which is artificial stone, say something like 10 mm coarse aggregate, its transition zone around, and then another maybe 12, 10 or 7 or 8 mm, if it is 20 mm down, 7 or 8 mm of mortar. I mean this is exaggeration, but it could be something of this kind. So, the aggregate of recycled aggregate has got an old ITZ and then mortar adhered to it, and then you will have new ITZ around it. when you put it into the concrete. So, now you have got two ITZ, old and the new, and therefore, the strength is still lower, properties are still lower, right. Okay. So, new ITZ, and that is your bulk mortar now, right. So, new mortar that you would be putting in. So, that is the scenario. So, let us go back now, I can go back now, this is the one. So, that is why what you can do, you got to remove this mortar as much as possible. If you remove this mortar around it, if you remove the mortar around it, if you remove the mortar around it, okay, this color is fine, mortar around it with the old aggregate, then it will be better. It will have, and remove the whole including ITZ completely, that will be best. Now, how do I do it? One thing we know, if I heat up CHS system and calcium hydroxide system, CHS breaks down up to 100 degrees centigrade. What will happen? 100 to say 200, H will go away, that is your capillary water, that will go away, capillary water will go away fully. But up to 400 degrees centigrade or so, this will start breaking, and 600 or so you will find that calcium hydroxide also breaks down, which means that bonding capability of this CHS will vanish if you heat it up. That is what happens in fire. When you subject concrete to, concrete is subjected to fire or high temperature, we subject it to high temperature, this is what happens. 600 degrees centigrade you will find the strength is very little, 800 you can just scratch it out. So, this therefore, if you heat it up, the adherent mortar will tend to go away. So, that is what they were trying, and they have tried heating and then rubbing, heat it and rub. So, concrete masses are heated to 300 degrees centigrade in a packed bed heater, and paste content is weakened to remove mortar and paste added to old aggregate. So, this is a processing part other than collecting, crushing, getting into the right sizes. Now, this is something more. So, ball mill crushing is followed to recover fine aggregate or powder for soil stabilization, and this is how the process is. So, it is in a packed bed system, concrete rubble, this will be heated somewhere in a packed bed heater, and then the coarse and the fine aggregate will be separated out. So, fine aggregate would be actually recovered, dust extractor. So, that is what it is, coarse aggregate recovered in equipment, ball mill, and recycled fine aggregate, recycled coarse aggregate, you can separate it out through a vibrating screen. Okay. There is another kind of electric rotor stuff method, this is another one, same process. It is passed downward now, crushed concrete lumps are passed downwards. There is of course a motor which would cause things to rotate, and it is passed, and this is one side of it, eccentric shaft is there, there is an eccentric shaft, and this rotates, and this crushes against the wall, crushes against the wall. This is an eccentric shaft which will rotate and crushes the aggregate against the wall, therefore causing some fine particle to come on one, fine particle, and coarse particle to, fine particle becoming finer, because it is eccentric shaft. So, one side it will have more, other side less, and crush them between the wall and the shaft wall. So, concrete is passed, this in the electric shaft rotor method, crushed concrete passed downward between concentric inner and outer cylinder. The former rotates at high speed to produce grinding effect to separate mortar from the aggregate. So, this will separate the mortar as much as possible. In the mechanical grinding method, coarse and fine aggregates are separated by small holes, right, in a partition plate. I will show the diagram, placed at an angle with center shaft in a horizontal rotating drum, where grinding is done with steel balls. So, this is where your drum is, right, and there are passing holes are there from this one which will take out. So, for example, this will rotate, recycled aggregate discharge would take place through somewhere there through this ones, right. There is a drum, this will rotate, and it has got steel balls, actually this is the balls. So, this is a kind of balls, abrasion of those steel balls with the aggregate system causes removal of the fine particulate system. So, there is another method of heating up to 700 degrees centigrade and expected to have only 2% paste adder after disintegration. So, that is what it is. Well, now you are heating it to 700 degrees centigrade, which means that, or 600 or whatever it is, you are giving additional energy. So, energy required to and then this must be accounted for. So, this is also high, and heating obviously would mean more energy and carbon emission depending upon from where you are getting the energy. So, that is the thing. So, the construction waste and demolition waste, CNW as we call it, construction and demolition waste, that has been processing is important, and still you do not get the best. There are other ways people have tried to use it. I think I might have, for example, what they have tried to do is them get the aggregate, put them in a fly ash water suspension, so that fly ash actually gets into they get inside the pores of those aggregate system with a lime fly ash system. So, try to improve the ITZ somewhere, people have tried this kind of thing, or put simply fly ash, which is fine, might get adhered to the mortar in the cement hydration reaction, calcium hydroxide produced. So, there are several things being attempted. Other ways are poor quality concrete debris that comes from the road, wood metals. So, if you separate out the wood and metal, you can reuse them if possible. And poor quality concrete, some of them can use in poor quality concrete, for example, not a pavement grade concrete. Glasses are not used in concrete because glass is attacked by alumina. In alkaline system, alumina system, glass may not be stable, right. Sodium silicate generally they may not be stable. So, alkali attacks generally glasses. Masonry of low strength concrete, that you can produce. So, not one use, you can use different use, you can make different use. Paper recycled and hazardous ones are handled separately. Papers, for example, they are recycled. If there is something hazardous, that you separate it out and handle it specifically, all right. So, demolished concrete lumps, I think I will stop after processing. Demolished concrete lumps, that is how it comes, goes to a jaw crusher, and then from the jaw crusher it can go to impact crusher, vibratory sieves. This you can use in road subways or backfill. And if it goes to vibratory sieve, straight away you will get the finer ones, then go to core crusher, vibratory sieves, low quality recycled coarse and fine aggregate. And if it is heating is done, then coarse aggregate scrubber, you scrub it out, fine aggregate scrubber, vibratory sieves, powder or the sand, high quality recycled and coarse aggregate. So, heating gives you higher quality, vibratory sieves first sieve it out, and impact crusher, this gives you low. So, you can separate out and use them for different uses, right, different uses. So, they have their aggregate classification. I will just quickly go through this, maybe we will repeat this in the next class, right. Coarse aggregate, for example, class 1, 2, 3, 4, 3 and 1, 2, 2 types, 3, 4 etc. What you see is properties wise water absorption, loss on weight, and this is other thing. These are the two things you see. I will just stop maybe. You put it in water, there can be loss in weight, absorption will be there could be loss in water. So, these are, if it is brick, source is brick, construction or demolition waste, you cannot allow more than 2.5%. Glass, very small quantity, plaster this much, inorganic this much, plastic this much, wood, total 1 to 6% of the impurities can be there, but otherwise should be all aggregate, right. So, European code has got their own, I think I will discuss this in the next class, right. So, if you have quickly any questions, I would like to answer.